We are very pleased to have tonight two special guests for our Outside Salon. Just a few words about Outside Salon. Outside Salon is, for those people who, I see a lot of really familiar faces, but Outside Salon is a series of events that happens roughly every month, sometimes more often, at the intersection of art, science, technologies, and we tend to have scientists being put together with artists and see what happens, or we feature long-term collaborations, which might be a model for other people who would like to start collaborations in art and science, and this, I think, is quite a model of collaboration. So tonight we have Dr. Mark David Hosale and Jim Madsen, who have been collaborating for quite a while on several projects concerning neutrinos. They will discuss the processes of collaboration of art and science projects, and in exploring the visualization and sonification of data sets collected at the Ice Cube Neutrino Observatory, which I believe is in Antarctica.
Right at the South Pole.
So, and you are going to do a talk together, I believe. So, without further ado, I am introducing you, and then we'll have hopefully a long and exciting Q&A. Okay. Thank you.
Okay. So, I give lots of talks, and so I am very happy to have people interrupt and ask questions, because everything I'm going to tell you I've said multiple times, right? And so I know it's coming, and so it's more interesting to hold a conversation rather than to have a monologue here. But what we're going to do here is I'm going to start off and spend maybe 10 or 15 minutes trying to give you a very quick introduction to what Ice Cube is. And I'll touch very little on the actual science. Ice Cube is really this incredible project that there are literally, I think one could say, dozens of topics, each of which could fill an hour, right? And so one of the challenges is how do you condense this down into something that makes some sense? So what we're going to do here today is I'm going to give the world according to Ice Cube, and then I'm going to turn it over to Mark David. He's going to talk about his efforts, and then we'll discuss how we worked together in these last few years. So this marker here is at the South Pole. Each year on January 1st, they put in a marker literally at the South Pole, but the ice moves about 11 meters a year, okay? So one of the neat things is when you're down there, you see these markers going off into the distance. There are people, believe it or not, who spend, for our project, 13 months at the South Pole. So the last plane left about mid-February, and the first planes are just arriving now, okay? So they are completely isolated from about mid-February to about the end of October. And one of the things they get to do is design the South Pole marker. So each year that's unique and designed and actually built. So I guess that would be an example of art science as well. And so they're really beautiful, and you know, depending on the interest of the people there, change each season. So go ahead, next slide. Okay, so, and we can go to the next one. Okay, so I also have to start here because I myself am not an astronomer, and so I just like to give you the broadest introduction to what astronomy is. And astronomy, astrophysics differs from most other sciences in that we cannot bring the thing we're interested in to the laboratory. And aside for lower energy things, we can't even reproduce the environment in which the objects we're studying exist, right? So in the most generic sense, there's some object out there that's hopefully producing something that we can measure, right? The first people used their eyes, right? And in the last century, really, we've basically made instruments that cover the whole range of light. The only thing special about what we call visible light is we can see it without an instrument, right? But otherwise, to a physicist, this electromagnetic spectrum is pretty much a continuum, right? And so we have instruments that go all the way down to the longest, lowest energy light called radio waves to the highest, shortest wavelength light we call gamma rays. Okay, so next slide. So again, just to kind of reinforce that, the reason why we do that is when you look in new ways, you get different information. So the idea here is I show you pictures of a hand in different with different instruments. So they go from an MRI, which is kind of like radio frequencies. The object next to that is the Crab Nebula in radio wavelengths, right? And then the next picture is infrared, and that, just like that's still a hand, that is still the Crab Nebula, but in the radio or the infrared. And then you get to optical, right? And it's a kind of a neat picture. But I think really the most revealing is the X-rays, right? And so in the same way, we wouldn't necessarily know what that internal structure was without X-rays. You can see this internal structure that's not at all apparent in the Crab Nebula, right? And so basically all of science is a quest to look in new ways, right? And in some ways, that's kind of what art is about too, right? So next slide. So there was an amazing sound that went with that, right? Because neutrinos make tremendous amounts of noise. So it turns out that was an artist, license. There's no sound associated with the neutrinos, although some people think that there's possible that you could put microphones down in the ice, and for very high energy neutrinos, they actually could record that. But it turned out there were other issues we could talk about why that's probably not very viable. But the idea of how you see neutrinos is pretty straightforward. The neutrinos themselves are absolutely invisible. There's something like 100 trillion neutrinos per second going through your body, right? And if you said you wanted to be a neutrino detector, on the average, it'd take about 100 years to have one interaction, okay? So if they don't interact, they make absolutely no impact, and they're invisible, okay? So one has to have some medium in which they'll interact, and that means it has to have protons or neutrons, and then out comes a charged particle, okay? And it could be an electron, which you're all familiar with, or these other two particles that are in the same family as an electron, a muon or a tau particle. Okay? And those are important because they have electrical charge, and when they are in a clear medium, they give off light. So the idea is very simple. You just instrument a clear medium, right? And you collect that light, and that will tell you about the neutrino that interacted, right? So you don't capture the neutrino, you don't capture the particle that's produced with the neutrino, you capture that light, and then you use your knowledge of that interaction to get the properties of the neutrino. Okay? So how are we doing? Does that make any sense? Because that's the easy part, okay? So now, to make that work is very hard, okay? Very hard. So people understood in 1960 that that's how you could do this. The only problem is they also understood because these interactions are so rare, you would have to instrument a cubic kilometer of clear material. Okay? And so just to give you an idea, a cubic kilometer of water or ice weighs more than all the people in the world. Right? So all the people in the world basically could fit in 1 kilometer by 1 kilometer by 1 kilometer. So it has to be something that's essentially free, right? Because it turns out that's 1 billion tons. That's how much water or ice that is. So go ahead to the next slide. What's that? Yeah. 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 So believe it or not, neither one of those two, right? So the neutrino comes in and it interacts with either a proton or a neutron. And so inside the atom in the nucleus, it interacts with one of those. Yep. Yeah. And then out comes the electron, the muon, or the tau particle. And we put the muon on there because we like those because they go a long way. They can go many, many kilometers through rock and through ice as well. And so they make a nice track that enables us to very precisely tell the direction. And if we're going to do a telescope, that's one of the things we're interested in. Okay, next slide. So how did we do this? All right. So as I said, literally more than 50 years ago, the idea was first proposed in a paper that you could do astronomy with neutrinos, right? Instead of looking for light, we would look for those interactions that would then tell us, looking backwards, where these neutrinos came from. So, and the first people who did this naturally thought of, and the paper that was written said, do it in water, right? But in the late 1980s, Francis Halsen at UW-Madison got this idea that maybe it could be done in the ice. And so it turns out at the South Pole there's infrastructure, right, and about like 2,950 meters of ice, okay? And so that's where we constructed, over the course of 7 seasons, the Ice Cube Detector. We melted holes 2,450 meters down, okay, about 60 centimeters in diameter. And each one of these we put 60 light sensors, okay? These are, again, any one of these topics I could spend a whole hour talking about, but these are incredible independent data takers, okay? They have clocks in there. They all operate so that not relative, but absolute, they agree to about 1 or 2 billionths of a second all the time. And so they sit down there on the ice, 60 in a string, between 1,450 and 2,450 meters. So they're 17 meters apart. It's very difficult to convey the scale. Here's the Eiffel Tower, right, to scale, right? So it's 3 times the height of the Eiffel Tower. The distance from one hole to the next is 125 meters, so more than a soccer field or a football field, right? And so altogether, there's 86 holes like that were melted, and then cable lowered down with 60 of those light sensors on, so there's over 5,000 light sensors, which sounds like a lot, but remember, this is in a cubic kilometer of ice. And so, yeah, go ahead. Yeah, so the water stays in the hole, right? And it took about a little 30 to 40 hours to melt the hole. And then in round numbers, about 20 hours it stayed open long enough that you could deploy it. It typically took between 6 and 12 hours to actually deploy it, a string. And then it freezes up. Anyone want to guess how long it takes to completely freeze? Yeah. That's what your thought would be. Oh, it's like this very cold ice, right? It's a cylinder that's 60 centimeters in diameter. How long could that take? But it's like months, right, before it all freezes in. Yeah. Why? Any guess why? Yeah, that's it. The ice is a very good thermal insulator, and for the water to freeze, it has to propagate the heat away, and so it basically is like a good thermos. Yeah. So. The ice is actually quite cold. It's about 45 below, roughly, at those depths. Yeah.
The pressure doesn't freeze here.
Oh, yeah, so that's another question. The pressure is extremely high, but this is like a 1 or a half-inch thick piece of glass that's in there. So, yeah. Yeah, the detectors are basically the size of a basketball. This active part is 10 inches across, or 25 centimeters, right? And so it's maybe 12 inches across in a sphere. Yeah. So there is a digitization system on board. So the signal is digitized there and then set up as a text string to the surface, right? These, for electronics, are pretty quiet, but they have a noise rate of about 300 hertz. So 300 times a second, they say, I saw something, even when nothing is there. So we have ways where we can ask the neighbor, did they see something, right? And then we have what we call triggers, right? And so we have a condition where, for example, we might have a 20 microsecond sliding window, and then we have conditions that we look in that window and say, did a sufficient number of detectors see some light, then that something real happened, so record that information. Okay. So in terms of like data rate, I'll talk about this in a moment. In round numbers, it's a little less than 3,000 times a second we record an event, which is not overwhelming anymore for modern electronics. Right? Okay.
Detectors or sensors. You said it's about 60 of them are placed in each hole.
Yes.
So are they all interconnected?
Yeah. So this cable that you see here actually connects to a main cable, and then they're connected in pairs, and so they have what we call a hard local coincidence, right? And then they're also able in software to look at other pairs to see, kind of a verification type approach. Yeah, and so it works out to be 17 meters apart on most of them. There's an inner area that's more densely instrumented that Ken works on, right? Yeah. Okay, go ahead. So what do we actually see? So what happens is the neutrinos themselves. There we go. Okay. Yeah, that works. Yeah. So the neutrinos are what we call ultra-relativistic. So they have energies, kinetic energies that are many, 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 many times their rest mass energy. Okay? And so the charged particles that are created that come out also are going extremely fast, essentially at the speed of light. They're actually going faster than light travels in the ice. Okay? So light slows down when it goes through another medium, but the charged particles are actually going basically at the speed of light in empty space. So again, what we do is we look at the sequence, and what these pictures show are how we represent the data. So these dots are detectors waiting to see something. If they see something, we color them in. Okay? And the colors are artificial. They're to show the time sequence. Red is where the first light was detected, and then blue is at the end. So here's our first test. If I ask you to describe what happened in this event, can you see right away from this picture, you can get a qualitative understanding of the event? So if I ask you to describe what happened here. Yeah. So it's a particle that started here and just zoomed through the ice, right? Right with your eye, you can say, I can tell you where that came from. What about this guy, though? It started in the middle and went out, right? So this guy, we can tell for this high an energy of a thing, we can tell to less than a degree where it came from. The problem is we don't know where it started. We don't know how much further it went. So we don't know how much energy it had because we only collected the light through this part of the detector, right? These guys we collect almost all the light, and that tells us how much energy it had, but it's very difficult to tell which direction because it's basically a spherical pattern of light. So these, we can get the energy very precisely, but the direction only to about 10 or 15 degrees. Okay. All right, so I'll just say this real quick. We see about 100 billion events in a year. 100,000 or 1 in a million are actually neutrinos. And out of those, 10 are very high energy ones on the order of that, 10 to 100. That was the original intent of the project. Okay, we'll go on here because I got to give Mark David a chance to talk. So here's what this would look like. An invisible neutrino is shown in red. Then it interacted, right? And then it went through the detector. Okay. And then if the light happens to intersect one of those spheres, right, it records that light. Actually, a very small amount of light, right? Most of the time we see a single photon. Okay? Go ahead, Mark David, because I got to move faster. So pictorially, this is what we are looking for. Most of the time we see a particle coming in from the southern hemisphere into the detector. That was from a cosmic ray shower. Okay? That happens, again, roughly 3,000 times a second. 1 out of a million of those is actually coming from the northern hemisphere, so we know for sure it's a neutrino, the only particles we know that can come through the Earth. And some of those neutrinos are very high energy, so we know they weren't created in the Earth's atmosphere, but they were created in a big explosion out in space. Okay, so next slide, and then I'll turn it over to you. Okay, this has been very successful, a very rewarding project, and so I think I'll just leave it at that. You can skip the next slide, and then I'll let you go. Okay.
Can you hear me if I talk here? Okay, good. Yeah, what I want to do is I want to kind of give you a very, very quick and, let's say, incomplete overview of a few artworks that I've done in the past, just to get kind of a sense of kind of work I do, and then talk about a particular series of works called Quasar, and that'll kind of lead into the story of how I met Jim. So first of all, one of my earlier works is a work called Defendex ESPGX, which was one of the things I'd point out is, I put in a mixture of like collaborations and solo works, and so actually I would probably say the majority of my work is collaborative. So I collaborate quite often with other people, whether artists, composers, scientists, what have you, architects. So this is a work that was created around the time that the Iraq War, second Iraq War was starting in the States, and it was definitely very much in response to what was happening there. It's not a pedantic piece, but it's meant to be kind of an experiential comparison between Cold War culture of fear and war on terror culture of fear. So it's infused with this space. It's like a network space of stories, in a sense that are not always kind to you. Like when you interact with it, it doesn't react the way you want it to, or sometimes it does, making you think it should work. Everything works, so it actually takes video of you as you're using it, and then it presents that to you. So there's a bit of a paranoid feeling about it. And this was a work I did with another artist, John Thompson. And we worked on this for about 3 or 4 years, intensely on it. A lot of my work, I think now is maybe a good time to say it. A lot of my work, I sometimes wonder what it's about myself, but I think it's about knowing. That's one of the things I really am concerned with, ways of knowing. So when you talk about Defendex, it is a kind of knowledge map in a sense. I see the software in there as a kind of way of exploring a territory. And so with this project, there's a kind of way of knowing, and it's a kind of a long story that goes into kind of various ways of computational thinking, like combinatorial logic and playing with narrative. So what it is it's a film that's presented on 4 screens simultaneously, and each screen you can set the story path and trajectory, so it can go forwards or backwards in time, but it can also move through the character space. So some characters become antagonists, some become protagonists, depending on which perspective you take. So it's all dependent on kind of point of view, kind of testimonial view of the story space. And it's a very musical piece in a lot of ways, because it's a lot of music and dialogue that kind of ebbs and flows in this kind of schizophrenic tapestry. I've done a number of collaborations with architects, and you'll see, I think, pretty much all the works I'm going to show after this are architectural. This is a project I did when I was a professor at the Technical University of Delft in Holland. I was working in the Faculty of Architecture there, and we were commissioned by Festo, which is like you might know them as like a very high-end tools manufacturer, but they also make pneumatic actuators, like for manufacturing, things like that. And so this was a display of something called the Fenway Effect, and we made this wall out of it, and the idea was to play a kind of game. So as people stood on one side of the wall, it would bend away from them, and whoever was closest, it would bend away from. So the person who's on the other side of the wall would get pushed away. And it was really interesting to work at this scale with such a kind of simple idea, but it's kind of a bit like playing with elephants. That's kind of the feeling. But this was shown at the Hanover Messe, and as you can see, it was a very large collaboration, involved 3 major entities, which was TU Delft, Festo, and a company that was involved with most of the booth construction, Burkhard Leitner in Germany. My most recent work is a work that was up for a year in the Marca Museum called the Homunculus Sakura, which is it's an array of 41 sculptural objects. The objects were designed in a CNC on a CNC mill, and then cast in a bio resin alternative to fiberglass. And even the material, we didn't actually use epoxy resin, and we didn't use fiberglass. We used an alternative, so everything was VOC free. We didn't need really any major hazmat suits or anything to build it. And part of the reason of doing it that way was not just because it was easier, but really trying to think about how we can work with new materials in an ethical way, and trying to move towards more bio-based practices, even in art. And artists are quite guilty, actually, of working with really nasty things all the time, and some of them, this is not a joke, some of them poison themselves and kill themselves. It's kind of an old story. So there's a lot of concerns in thinking of it. The piece itself was originally commissioned to be part of a landslide, a group exhibition called Landslide, which was a bunch of pieces at the Marca Museum dealing with urban, suburban, and farm issues around the GTA. So my piece in particular is engaging thoughts about ecology and the green belt, and even the layout of the piece was a reflection of the green belt. It is meant to be a kind of collapsing of scale, and you'll see this is another interest of mine, which I think relates to how science works. You collapse scale into the realm of our perception so that we can actually see it. Otherwise, it's beyond our intelligibility, and that is a kind of way of knowing. So we collapse the scale of the green belt into the space, and there's a kind of ecology running through in the form of sound and light, and there's supposed to be a sound there, but and some of the pieces, the ones I'm standing next to there, are touch sensitive, so you're actually able to kind of affect what is happening in the ecology through your touch. So that's a kind of quick overview. So I'm going to talk about quasar. I'm going to run through this kind of quick, just so we have some time to say what we want to say after this. But so quasar was a series of works that I realized with an architect named Jean-Michel Crétaz, who was at the time was at the Southern California Institute of Architecture in Los Angeles. And how I got involved with the work really late in the project. And what happened was Jean-Michel, Aaron, and Dooley had kind of designed this piece. They thought of it. It wasn't really manufactured, but they didn't really know how to make it work. So I came on board and I joined the conversation. And through the conversation, let's say, certain elements change. And that is because, you start to realize, let's say, that on one hand, the power of working with computation and art, the ability to work with dynamic systems, interactivity, things like that. But also there's a number of limitations. Like, for example, at the time it wasn't very easy to light up. I think for this one there's something like 80 LEDs and have like real-time control and all this. It wasn't really that convenient. We did find, however, an off-the-shelf solution, but it had to be hacked quite heavily. And where things really started to progress in terms of my involvement with the collaboration was when we really were looking at the behavior, the sound, and how these things come together. And it became very obvious quickly that I wasn't just there to make it work, but I was actually having a huge influence on the results of the work itself, the artistic content. And this, so this piece showed at SciArt for I think 6 to 8 weeks in 2008, and it's called quasar. One thing I didn't say is why quasar? Well, quasars are these, and Jim, you can chime in, but quasars are these massive astronomical events that we can see, and they're so big I don't think you can really imagine them because they're billions of light years across, and but they're also some of the brightest and craziest things we see, right? When we look out there in deep space, and we don't really know what they are. And for I think for Jean-Michel, when he named the piece, it became this kind of thing that was iconic of the limits of knowing, in the sense that we can see what we can't see, and it becomes this kind of event horizon in the let's say limits of our existence. As part of this piece, Jean-Michel had some contacts with SLAC, which is the Stanford Linear Accelerator. Yeah, and they loaned us this piece of equipment, which I have to say, for me, on first sight, didn't look like much. But what this is a muon detector, and it detects muons in 3 directions. And so, as part of the piece, part of the interaction, we had like a touch screen, we had capacitive sensors that would sense your presence in the space, and we had this muon detector. You can see it glowing red up there in the top right, and it would actually detect muons and trigger sound and light events in the piece. So it became this medium for communicating with things that you would otherwise never be aware of. We had here's where I'd probably speed up. We had the opportunity to remount this. So I should say that, from 2008 to 2012, Jean-Michel and I had a very close conversation. We even tried to mount several other artworks, and for many reasons we're not able to. But we met, I think, quite regularly, like every 2 to 4 weeks. We were having very long conversations about art, life, philosophy, what have you. And even around teaching, I should say, I taught in his program several times, and that was through this collaboration. And so this piece didn't just emerge out of a single opportunity, but really out of this very lengthy conversation around ideas. And so it was at the central event at Nuit Blanche in 2012. It was a group exhibition in the parking garage in Nathan Phillips Square. And this is some video of it. And there was a number of innovations. I guess it wasn't a very long video that I went through, which I'll talk about in a second. But as you can see, in a lot of ways, the topology is similar. However, we're using a better material for the light display. So I'm going to turn the video off. It doesn't matter. This event was quite interesting because we attracted probably 85,000 people on this one night, to see it. So, I mean, it's kind of unheard of scale. And yeah, well, there's a thing, I won't get too into it, but there's a thing that goes on in Nuit Blanche. You get these kind of different crowds. So the early crowd's serious art goers, and then around midnight, loving. Everything's good, and it was actually well received by everyone. But then you get really serious art goers around 5 in the morning, because that's when everyone else is sleeping in the streets. But I mentioned the muon detector for a reason, and one of the things that happened when I was around the time of the first quasar was I was giving a talk very much at a salon very much like this one in Santa Barbara that was really for a more mixed crowd. It wasn't an art science salon, but something like for crazy artists, scientists, engineers, and it's still ongoing. It's quite a wonderful event at a place called Fishbone. And I was up there talking, and I'm like, okay, and we have this, and pay attention to what I'm saying right now, muon detector and whatever, blah, blah, blah. And I'm just trying to talk about the best I can. And there's this guy in the audience. He's like, look, that was really interesting, but, you need to learn a little bit more about the science because, first of all, it is not a muon detector. It is a muon detector. And by the way, I've been to the largest muon detector in the world, and it is in Antarctica, right? And that stuck in my brain, right? So then we had this opportunity to do Quasar 2, and we're like, oh, what are we going to do? We can't get a muon detector because we cannot get one from Slack, and where are we going to get one? And it's kind of central to the piece. So I just started poking around, and then one day I emailed Jim, and I said, oh, I have this piece, and I was wondering if we could use your data in the piece. And he's like, what is this? And by the way, our data is intellectual property. And but we got through that very quickly. And so, at the time, it was very much like, what is this data? And we had a lot of conversations about just trying to understand what's going on and how to really map it to this body. As I mentioned, there are a number of innovations. This is important later, but, one of the things I do as part of my artistic practice is I develop software and hardware systems. So one of the things I developed for Quasar 1 was more off the shelf. It was very clunky, didn't work as ideally as we'd like. For Quasar 2, I developed this system called the ND node, which allowed me to network 97 microcontrollers together in a system and control all the LEDs, and also have sensors, so it does bidirectional, does sensing and sending. Just a nice view. Shortly after Quasar 2, we had an opportunity to present at a number of things, but the idea of mounting the entire Quasar 2, I didn't mention, but Quasar and Quasar 2 were about 10 by 10 meters in scale, so quite large, requires a big truck to move around. So we decided to make the kind of laptop version of Quasar. And So that was Quasar 3. That wasn't the only reason to make it smaller, but we showed it at, like it says there, in Montreal, and we showed it at York University and at the in Wisconsin. And one of the things about Quasar 3 was there were some screens, and this is kind of an upgrade from the screen from Quasar 2, but one of the things is what's going on here. So we, on the left screen, we have kind of hard data. So I'd say it's like a hard visualization of data. On the right screen, we have a kind of more, let's say, creative visualization of that data. In the middle, you have the body itself. So you can see how kind of the mind, the left brain and the right brain is how we referred to it, kind of come together on the body of the piece. And on the left, what we have is we have not only data from, by the way, you can't get real-time data from Antarctica if you hadn't figured that out. So we did data dumps. So we have, we just picked a year, and in that year, we have mostly ice top events, which are cosmic ray events, which are the muons, and then, or the most common muon. And then we have weather stations, because again, we're really interested in this idea of collapsing of scales. So we have the cosmic scale, cosmic rays. We have the weather, which is kind of the ambient, the atmospheric, and then you have the personal. Where that comes in is on the far left. There is the log reports that get dumped from the Antarctica, and mostly what they are is uptimes for servers and things like that. But you also have tidbits in there, like the holiday party, or little things that kind of bring in this kind of human element, and it starts bringing the piece back in. So it's really trying to connect the mind, the body, the self into this kind of like larger and really projecting out into the universe. It's kind of the goal of the piece. Yeah. So that's kind of where I leave it. This is how probably you remember seeing it. And so now I think Jim and I are going to sort of talk together. Jim, you're going to talk again about.
So we have a few more slides that we'll show. So go ahead to the next one. So my interest was in producing a more literal model that would explain how the Ice Cube Detector worked, right? So I was working independently on a system that was scaled down. So there was one vertical string of LEDs for each of the 3 strings of light sensors in the ice, and instead of 60, it only had 20, right? But the idea was to make something that was portable, and our first efforts at that were, it was portable in the sense it would fit in the back of a minivan, but it probably weighed 500 pounds, right? And it took a half a day to set up and so forth, right? So I won't go through all the details, but we ended up now, we have one that has one LED for each of the 5,000 sensors that we can set up in an hour. If we go to the next slide, I think, it has sound in it also, right? So the center one there is a little video, and you can see that it has 2 things going on. It has a mock-up of background events, and then if you look here, Mark David did this clever thing where we have a position sensor, and when somebody swings their hands across the position sensor, it triggers one of the high energy events, right? And so it's actual data slowed down 1 million times, right? And then in the sequence with that same light mapping. So it's a visualizer. And we actually have it now. We have a 2-dimensional version of the program so that we can analyze events, because the events can be tricky. And so there's literally 100 billion events, so it has to be looked through by the computer, but in the end, many of them have to be studied in order to make sense of them. So we have software that does that, and the neat thing is now we have that software, so it will control that display, right? So it will not only show up on the flat screen, but it's basically like a three-dimensional monitor where each LED is one of the light sensors. So go ahead to the next one. And so I'll let you say what more, but we could probably.
These are just some
Yeah.
images like planning, what goes into it. So this is actually using neopixels, and for those of you who care about that sort of thing, but there are an LED string that in each LED there's a driver, and you can talk to it through a one-wire communication interface. So all this stuff I did for Quasar is unnecessary unless you want to spread it out over a building, then that's another story. But so it's not useless. But in this case, what I did for Quasar wouldn't be helpful. So, and then we used like teensies, and so a lot of it was we didn't have to do from scratch other than some custom circuitry and software. And yeah.
So this is just another image with the student that's on there. Yeah, yeah.
Well, this is just, I don't know. These are a little weird order, I guess. But this is our latest iteration, which is the version that Jim was talking about where you can trigger things. And these are just more conceptual drawings, but we were trying to connect the display to something called Neutrino World, which we'll show in a second. But maybe we'll just jump ahead. I thought might be interesting for you to see a quick demo of the Sonification tool. So, yeah. So I have, that's, no one knows who that is?
Yeah.
Famous artist? Yeah, I'm not teaching, right? Okay. Okay. Okay, so basically this is one of the things we developed, and this became the Sonification tool. It's quite simple and straightforward. It's a granular synthesis machine, basically made in Super Collider. And what it does is it maps events to this grain cloud. So what granular synthesis is it's a kind of synthesis where you make clouds of sound using little particles of sound. So it's a nice analogy to what is happening in terms of this light moving through time. And so what I did was I mapped each sensor in the array to a grain, and they're positioned in a stereo field. And so as you should be able to, hopefully if it's working right, hear the event moving as well as you hear things like density. And the theory is visual perception is very dominant in the sense that we are very attracted to things we see and we're very aware of them. But actually our oral perception is much more accurate. So we hear things very, very clearly and distinctly. And the ideas that I had with this was that if we could combine, and it's not revolutionary, but if we can combine sound events with the visual events, that it actually might lead to more accurate identification of what's happening. So this is still kind of in the play stage, but are we going to hear anything? No. Okay, this might have to do with the software I'm using, but basically the way it works is I had 28 events to work with, and when you click it, I think you heard kind of an example before anyway, but we can look at it later if you want to.
So just then another example, we have collaboration meetings twice a year for the Ice Cube group, and 2013 it was in Munich. So Mark David and Jean-Michel had given a talk at the Ice Cube meeting that was in Madsen. And so the host of that meeting in Munich said it would be nice to have an art-science discussion. And so we came up with this theme of science and art, and we brought in people, and they came in with these images, and the idea then was to have a discussion, which of these are science, which of these are art. images. Okay? Any guesses? So, like this guy here, science or art? Yeah. That turns out that's like shells, right? Right? How about this one? That's science. That is, if you know about scanning tunneling microscopes, that's an image from a surface map, right? Yeah. How about this one? Yeah. Maybe turn off the light so we can see a little clearer.
No, but in the sense that you can't really say because a lot of the terms are the visualization is a form of art.
Exactly. Yeah. No, it's a silly exercise actually, to be honest. Yeah.
Because it really it was our perception.
Yeah.
Our assumptions in general about what is science, what is art.
And also, most of you never even heard of art science, so it was a nice entryway into a deeper.
How about the upper one up there? Anyone seen that image before? That's what it is. Yes. Yeah. Very good. And then this one is actually Mark David's, right? So it was interesting. We had a panel discussion and then opportunity for questions. So we'll go there. This is the neutrino world. I think that one actually got put in sideways, but then So the idea is Mark David has gotten very interested in this property of the neutrinos that they change from one type to another between when they were created and when they're detected. Okay? And in between, they have this bizarre quantum property that they exist as all three types at once. So the idea is these balls that are flying by and spinning and simultaneously like three colors are representing the neutrinos, and then the other objects are protons and neutrons. Okay? And then if you hit the E, right, then that's an electron neutrino. And remember we said that's a ball of light, and then do a T. That's a tau. The tau has two interactions separated by a distance dependent on the energy. And then we have the muon, right? And remember that was a track across there. So that's an artistic interpretation of that neutrino world, right? And so if we go to the next slide then. Can you speed it? Yeah. So there's sliders. It's quite neat.
Yeah, part of the reason. So one of the things we didn't know what we're going to get into. Now this is the last slide. Now is this good at any time? Most of the stuff is built, let's say, via Skype and the internet. So we don't really see each other very often. I think the last time we saw each other was 2013. Right. Yeah. And so, like this whole display. And so, Jim's over there building the LED display. I actually designed the circuit boards, the interconnections and stuff. And, I did rub my rabbits full a little bit, and it did work. So, but, like with the software, so I send things. And so if you go in, there's always this control panel, everything I send them, that they can tweak every little thing, to their liking. And so, part of the collaboration is just trying to figure it out. And, and so, but it's also part of a conversation. I mean, the reason I wanted to do this was actually so we could build a bigger conversation. So one of the things that Jim and I wanted to talk about is we actually meet weekly. And there's actually a lot of hard work that goes into and sometimes we're just talking about, kids or whatever, or university politics. But yeah, a lot of it is just about putting in the time to get to know each other. And, where this is kind of leading is to some bigger, more ambitious projects. So, I don't know, not to ramble on, but one of the things is, like with the display, one of the things I get really excited about is it started off kind of as a science fair thing, something for education and outreach, but now the precision is getting so precise, like Jim was saying, that now that we can connect it to this steam shovel software, now that it's real time, it has the potential actually to become a tool, like with the Sonification, for analysis of events. So that means that the art starts to become a scientific instrument, that the playing with the perception and playing with the refinement of that is actually could, I can't make any promises, but could lead to discovery even at some point. And that prospect is very exciting to me. Yeah.
So, and I think, this will be my concluding statement, and then we can take questions. But, to me, what's been interesting about the journey is we're getting closer to this point where we can really immerse people in the world, right? So rather than being an outside observer looking at the detector, our conversations go along, how can we make somebody experience the quantum world, right? Not as an observer, but maybe as an entity within that, right? What are those rules? How would we, give attributes to people that as they walked around, it would mimic in some way what happens to particles, right, as they interact. And so, and all these things are stages and probably not doable in one step. I wouldn't say, right? And so it's, we have the luxury or the foolishness to keep talking to one another, right? And working on this, but partly what drives that are these intermediate, events and successes that keep things going. So we can probably turn the lights on and grab questions. Okay. Okay. Yes.
So the very last thing you said was to get people interactive stage control. The truth of the matter is that there is a significant value in learning to think in an abstract mathematical way. And that is the way you really look at the control. But then there is, of course, the truth that if you have the ways of visualizing that, and you can maybe consider the conclusions. So there is no doubt about that.
Yeah.
So, where do you draw this line?
So I think, so I'll say something, and then you can say you didn't understand what I said, if I'm misunderstanding what your point. So I think that there are some things that are, in some sense, purely mathematical, that any attempt to express them in another way is just less, right? And unfortunately, a lot of particle physics is like that, right? But there's kind of a hierarchy, I think, to the behaviors that are unique and absolutely contrary to our what we call classical world, the world that we experience, right? So I think that there are ways that some of that can be communicated that might motivate people then to go to that next step of saying, and if I really want to understand this at a deeper level, then I have to invest the time to learn this new language, right? So that's kind of what interests me is, as I say, for example, just this idea, how do you convey to somebody that an object in some sense exists as three objects simultaneously, right? There's no classical thing that behaves in that way. And but yet when it's detected or created, has to be only one of those things. Yeah. So, but it's a good point. Yeah.
Can I make it somewhat more simple?
Yeah. Sure.
So, I'm an artist myself.
Yeah.
And I always struggle with that kind of concepts with the artist side, where mathematics is in. And I think that mathematics for our human brains are a kind of proportion. They are just numbers. Imagine on another planet, other beings will not think with numbers. Numbers and mathematics science means applying this force, this quantity, with this kind of other something, you have on the other side this phenomenon. So this equals this. But this is just quantity. Mathematics is quantity. So let's imagine somewhere on another planet, another being is not thinking with quantities, he's thinking just with colors. Apply red plus blue, you obtain this, another color. This is still the world, represents the nature, but not with quantities, numbers as written, but with colors. On another planet, it might be just sound. It's still the world out there, so we can write Einstein E equal MC squared with colors. We can write them with sound. We happen to use quantity, and we call it mathematics. I don't know if it makes sense.
Well, I can agree with that because to me mathematics is not quantity. In fact, mathematics is abstraction and it is concepts. So to me, actually, if there are intelligent things somewhere else, there is a much higher chance that they're going to think mathematically than so.
That's a famous assumption which has never been tested.
About other creations, thinkings, definitely.
On the other hand, we think about, we are thinking about mathematics right now, but that's because your field is mathematics. But if I think of my own field, I can think of other concepts that are extremely abstract that I can't explain in other ways, and that I don't know how to convey. And so, and I'm in the field of the humanities and social sciences, so I think that all disciplines have these problems where items that are too abstract or that are too complex to convey.
Ineffable.
Like that's the ineffable. So, is there? But then, the question that you are asking is there a way to convey them? Is there a way to translate them into other dimensions?
I mean, for me, it still comes down to this idea of ways of knowing. Like I touched on a lot of things, but, mathematics is a kind of knowing, and there's like a philosophical way of knowing. And there's this kind of knowing that what Jim was touching on at the end there, which is really gets into this kind of more corporeal and visceral way of knowing. And it's a kind of gets into things, areas of like intuition and expression. And I do think there's ways to understand the world through that, even like, deep, complex concepts. Not that one is better than the other, but really finding these ways. And it's, one thing it can do is kind of hook people in, right? Like Jim was saying, but can also help share with the world ideas that, are really beyond them in their current form, Yeah.
Okay, I have a question. Were there any phenomena that you want people to understand until you were able to visualize it? Or, were you always able to understand what was going on without visualization?
So that's a good question. We have a class of events we call unreconstructible, right? So if you have 100 billion events, you have to have an algorithm that will sort through, right? And fortunately, the majority are classifiable, and analyzable, but still thousands of events fall into this category of it confuses the reconstruction algorithms. It turns out if you look at those by eye, people are very good at seeing patterns, and they go, oh, the problem is there's 2 particles going through at once, right? And it turns out we now have algorithms that will sort and look, because the detector is so big, that happens a few % of the time, or 10% or something on that order, right? So we have to be able to do that. But it also happens now that sometimes 3 particles go through at once, right? And then a 2-particle algorithm will not make sense out of 3 particles, right? But what we did, interestingly, is one of the postdocs at Madsen said, I want to do an internship for high school students. And what she did was had them look through these unreconstructible events. And they got, so they would say, yeah, this one's 3 particles, you know, this is 2 particles. And so that's one kind of simple example. You know, Ken here works on the lower energy stuff. And I talked about that there's actually a more densely instrumented part. And interestingly, originally, having more information was confounding, right? You didn't get, your thought would be, if I had more light, I must be able to reconstruct the events better. But unless you have the right tools, that was not the case. Is that a fair statement? Not what you mean by low energy. So the energy scale, and Ken's really the expert on this, but the way I like to explain it is, let's call a chemical reaction a unit of 1 energy, and that's rearranging electrons. If you rearrange the protons and neutrons inside the nucleus, that takes 1,000,000 times more energy. Whether it's a fusion, fission, or radioactive decay, it's all about the same, about 1,000,000 times more. So the Ice Cube detector doesn't start to see particles until they have about 10,000 times more energy than a nuclear reaction. Okay, and those are the lowest energy ones we can see now, and they go up to being, peta, 10 to the 15th times, you're right, 1,000 trillion times more than a chemical reaction, right, in one event. So.
The neutrinos that you can feel. Ouch!
Yeah, exactly. There's a question way in the back. Yeah.
I'm curious to know how you view your role as an artist in a partnership like this. Is it more about finding better, more beautiful, more accurate ways to visualize the data, or is there also sort of a symbolic component to what you're doing? Is there some editorializing as well, or is it really just about representation?
Well, outside of Quasar, I mean, I feel like a lot of this work is really still building. And in some ways, I mean, this is a normal way artists work, I think, is I don't know what I'm building exactly. Just that, I mean, we're going to make something, and I think when we do, it'll be art. We're going to make an art thing eventually, and it'll be a real collaboration. So I'm not going to just rely on Jim for consultant. But, I mean, it sounds really vague, but a lot of the work we're doing is really collaboration building and conversations. And not that I don't feel like Neutrino World's creative, or, you know, I'm not, or I'm not even dismissive of it, but I'm not sure it's at this stage what I'd put in a gallery. Now, maybe I'd develop it further, and it would be something I'd want to put in a gallery. But at the moment, it's like, to me, a conversation. It's like a very long conversation. But in terms of the LED array, that is starting to grow. So we are thinking about next stages. Jim wasn't sure if I wanted to talk about this, but next stages. So where I want to take it, and we've been working on grants even for this, is, or we want to take it, I shouldn't say I, but is actually trying to develop a volumetric display. So there's a few techniques, you know, and like one technique we're looking at is what's called a swept volumetric display. So basically you spin a bunch of lights or LEDs or whatever, and you can actually make something holographically float in the air in front of you. And from the science point of view, what is interesting is you can actually start to not just view it as is in a space. We have the cubic meter, as we mentioned, which is a stepping stone to this, but you can actually start to scale the data and zoom in and really look at it. But I'm also thinking about it as a sculptural tool, like something I can sculpt this. One of the things you might notice I like to do is sculpt with light. So it's another way of exploring light and sculpture, but I'm not really sure. It's all a bit speculative. We don't even know if it'll work that well. But around that, we're starting to kind of step up the science behind what we're doing in terms of we want to conduct some user studies to actually see if this kind of display can lead to better identification of events than a standard screen, and maybe see if that going forward even makes sense in that direction. Yeah.
The other thing that I'm interested in is how do we engage students? The students today are different, like every generation is different, right? And they have a lot of visual stimulation. They're not necessarily, excited with the same approach to instruction as when I was a kid, as we say, right? And so what we're working on at very early stages is to take some of the tools that Mark David has developed and use those rather than saying, let's get the students involved in research their first year, which is difficult to give them a meaningful problem. We say, let's take like this display and then have them create on that, right? So have these tools. They can either add and do something literal like let's figure out a way to enhance how we display this, or it really is a three-dimensional display that they can create anything with, right? And do sound and lightscapes. And so I think that always the challenge is coming up with a real reason to interact, right? And always people will say, why don't we do more cross-disciplinary things, right? Why don't the mathematicians talk more with the physicists or the artist or the things like that? But if it wasn't for Mark David's persistence, right, it's not, as you can tell, I enjoy this interaction, but I didn't have the idea, right, that would have caused us to come together. And then he has the continual, this vocabulary and this process that's, common in the art of continuing to, explore until something develops, right? And so I think it's a great example, right, of it is tough. It takes a lot of effort. As you say, if you think about, we probably, the equivalent of a few hundred hours, right, that we spend one-on-one outside of the time we spend building the things that we talk about, right? So over this course of time. So it is not an insignificant amount of time, but I think you would agree it's been very fruitful. So, yeah.
I think there's a perfect continuum between art installation and an out.
I mean, I do this stuff.
They just say,
when I'm talking to physics, I call it art when I'm talking to physics. It's exactly the same.
Yeah, exactly.
So I'm picturing a big bank lobby
with a whole bunch of strings of
LEDs hanging
where,
blue crowds walk by and fun events are being displayed in Antarctica.
It's cool.
Exactly, yeah.
And it must be about the most fun thing there is.
Yeah.
I mean, what fraction of the neutrinos are you actually seeing? It's just this infinitely microscopic fraction.
Yeah.
So to see such a thing
is
just so cool in itself.
It is.
It's hard to believe it's even possible.
Exactly. Yeah. I always, as I say, I can give talks on many of these things, but I usually introduce and talk about all the virtues of the neutrino, and it has this incredible ability be created, and it's the only particle we know that, for example, will escape from a dense medium, right? So if you want to know really what's going on inside the sun, you measure neutrinos, right? Because the photons that are created are absorbed right away, right? And the light we see from the sun comes from the surface.
Totally correct where you propose that a particle could never be seen.
Yeah, that was the Pauly.
Almost true.
Yeah, exactly. And it's a fascinating subject in multiple ways, and just in terms of the history and then showing how long it takes to resolve it from a science standpoint, and then how once you have that, then it becomes a technology, right? It's while we study the properties of the neutrinos themselves, really we're using it as a messenger particle to learn about the universe, right? And you can't do that if you don't know about its.
Now you're trying to bring the neutrino into culture.
Yeah.
You're trying to show it to people. What more difficult thing could there possibly be?
Yeah. Well, it's reached a level that from a science perspective has been legitimized. The Nobel Prizes were for neutrinos this year, and then there's a new prize, which the name of which escapes me, that Mark Zuckerberg and friends have put together, and in physics it was given to 5 neutrino projects.
Every member of the group with 1,000.
Yeah, exactly. But there's worse things. Right?
I like the idea that all you need to do is get these neutrinos out there where ordinary people, can see them in some sense.
Yeah.
On the street corner, or one of your little cubes sitting there.
Yeah.
In Antarctica.
Yeah. Well, you're the right guy to talk to, I can tell. Most people say, "Why are you doing this?" Yeah. So I also brought some postcards. You can take home a season's greeting Ice Cube event card, right? It says, "Wishing you a new year of exploration and discovery." Okay. I have Ice Cube stickers, right? Yeah. We do have T-shirts, right? We have a T-shirt with this graphic on it that says, "We make neutrinos cool." Right? Okay. All right. So you're welcome to come up and grab some of these. Yeah.
About the sun, and you mentioned that if you really want to know more about the sun, you should look at what happens inside the sun.
Yeah.
Somewhere I've learned, I might be wrong, one photon starts in the center of the sun and it looks for million years bumping until it reaches the surface.
Yeah.
Which version is true?
Yeah, that's true. Yeah. But the neutrino, and so if you want to learn, I'm actually quite skeptical of that literal picture of a photon bouncing around and not being absorbed. But is that it's absorbed and re-emitted so it's not the same photon, right?
It's the same as picture of the sun taken in neutrino.
Yeah, and so again, it's an incredible history because back in the 60s, people came up with ideas on how you could look for the neutrinos from the sun, right? And they're absolutely mind-boggling experiments, right? Where you literally get one nucleus of an atom that absorbs a neutrino and then becomes radioactive, and literally out of this, how many 100,000 gallons of cleaning fluid, something like that, there's one atom that they can detect per month, right? And from that, they found that the number of neutrinos that they were measuring was not what they expected based on the best understanding, right? And so that was either the sun wasn't really behaving the way they thought, or the neutrinos weren't behaving. But nobody thought of the latter case for quite a while, right? And ultimately, that's what the Nobel Prize was awarded for, is this idea that the neutrinos, because they have mass, they can change from one type to another between when they're created and when they're detected. And so they are only measuring one type of neutrino in that experiment, and they were expecting that that was the only kind that was relevant, but actually some of them were changing to another type, so they were invisible to the detector. So that's why they were measuring fewer. But it took a long time, decades, to sort that out. Ken can probably answer that better.
Okay, so suppose one of them is 0. Do we have upper limits?
Yeah.
Fractions of an EV. Fractions of an EV.
Yeah. But here's the most incredible number I've heard recently, just at the last collaboration meeting. So, is it okay? Can I write on the board?
It's a math issue.
Yeah, okay. There's no chalk, though.
over on the side there.
Okay, yeah. So what we know is that there's 3 types of neutrinos, and I won't get into why this is important. And then there's another way we can represent them. There are 3 mass states, okay? And so what we know is what's the difference in mass between these states, and there's 2 possibilities. It could look like this, 2 that are close to each other, and then one up higher, or it could look like this, right? Like that, right? We know what this splitting is. It's the same here, and it could be in that order. So this is called a normal. That's called an inverted. So the neutrinos are almost massless, right? But to give you an idea how many there are, right? So again, to give you an idea what do I mean by they're almost massless? They're like 100,000 times at least less massive than an electron, right? Maybe probably 1,000,000 times less than that. There's so many neutrinos. If this is the case instead of this, it's like there's a whole other galaxy in the universe. That's how much mass difference there is. Even though each one is almost insignificant, you take a huge number times an almost 0, and you get a pretty damn big number, right? Like the mass of a galaxy. So I had never heard that. So you look and you say, what difference does it make if it's this scenario or that scenario? They weigh hardly anything. Why does it matter? It would be, if it's this scenario, it's like there's another galaxy in the universe, right? It's really.
The neutrinos weigh more than the star.
Yeah.
And that corresponds to the right-hand side.
Well, so this is just the difference in mass between them. There's still, because there's so many neutrinos, right? It's really quite an incredible thing. So.
You can miss half the mass of the universe.
Yeah. Well, we missed 95% of the universe. So, yeah. So, yeah. Yeah.
When Mark David approached you, what made you interested in collaborating with an artist?
Yeah, so here's the very good thing. So I will tell you 3 amazing things about the Ice Cube Detector, okay? You almost never hear this about any human endeavor. It was built on time, it was built under budget, and it exceeded the design specifications, okay? And because of that, I have a job, okay? Because they took some of the contingency money and they said, okay, we will create a job we call the associate director in charge of education and outreach. And so that meant there was somebody who had time, if somebody contacted, that they could interact. Because again, it's not that people aren't interested in interacting, but they don't, if I'm sure Ken would be interested too, but he's got grants to write and classes to teach and things like that. So the neat thing about my job is for the first several years, I was just out looking for ways to collaborate, right? And so rather than it being a problem, it was an opportunity, which is one of the things that I learned is it's almost impossible to convince people to do something that they don't have another reason to do already, right? So even with this tonight, if we had announced that we were going to give a talk on revealing neutrinos without it being part of the Art Science Salon, I can guarantee you from experience there would be 5 people here, right? It's
we're here for.
Yeah, but because you have an audience that's interested in this, right? Then we're meeting a need, right? And then it's a win-win for everybody involved. But it's very hard to start from scratch, and that's, as I say, and that's the persistence, I think, on both sides to make this a success, because the easiest thing is to say, that didn't work, and move on to the next thing, right? Yeah. But it's a great question, because it's because we had some resources that we have a bit, but it's like literally one person. Yeah.
What was the impetus then to put the money into an outreach and education program?
So so the question was, so why was the decision made to put it in that? And so that was really the project director's decision. So everybody has control over certain pots of money, and he made the decision that in the long run would serve the project well, right? And so I get to do all kinds of interesting things. So I'm at an undergraduate institution. It turns out that if you involve undergraduate students in research, that's outreach. Okay, so I do that. We send teachers to the South Pole. I have a teacher going with me in January, but we've had 7 other teachers go to the South Pole and work on the project. We've got 2 more selected for 2016, 2017. And so it pays huge dividends, right? So I think it was a good investment, but again, I'm very sensitive to what is the main purpose of what people are doing, and the reason it doesn't happen more is mostly you're evaluated on other activities, right? And so, and that's, I tell you, I have to bring this guy with me. Because, yeah.
What we call scientists.
Yeah.
We not have diverse.
We spend all our time trying to sell that.
Boring.
Yeah.
You want to come again? We have another one next week. Actually, one of the speakers is here. And
big data.
And we're going to talk about big data and artificial life and networks and this is going to be part of this is going to be outside one and laser. We record everything. We want also to do outreach internationally. We are part of the of an international network called Laser, which is part of the Leonardo network. And what? Sorry.
What's it stand for? Art, science.
It's the Leonardo Art and Science Rendezvous. They are happening everywhere in North America and in Europe too. Yeah, also in London.
In the UK.
So yeah, we're trying to connect all the forces and do a lot of recordings. So that's why we record everything. We put everything on online, and hopefully we'll have more people listening to us, and
there's a Facebook page.
more people interested in participating, like creating a big network.
So how long before we will see on the...
I don't know. Fields will put this talk onto their server.
I think it's going to be like
Pretty
almost
quickly.
immediate. Quickly. If you go on the Fields Institute website and you /live, you can find there's a link to archives. As soon as that is recorded is, well, give it like a 1 week because I think that the technician has to go through a little attitude because of the voice levels, and then they will put it online. So again, another round of applause for